In the good old days, Haskell had exactly one mechanism to derive instances of type classes that programmers were too lazy to write. And I mean, that was a very limited, but nevertheless very useful mechanism. So people tried to extend it in various ways. And so originally they made it work for more type classes because that mechanism is limited to just a bunch of built-in type classes. But later, there were also completely new ways of deriving type classes being added. And so these days, GHC supports 4 different ways, not completely different ways, but different ways to derive different type classes, and even has a language extension called Deriving Strategies that allows you to explicitly select one of those ways. So in today's episode of the Haskell Unfolder, we're going to try to look at each of these and discuss a little bit what the original motivation is, what use cases are, what possible limitations are, and so on.
Yeah, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we'll try to show them on screen and discuss them.
Yeah, okay. So the 4 mechanisms that exist are called stock deriving, Newtype deriving, Anyclass deriving, and deriving via. And the order in which I've given them here is essentially the order in which they've historically been introduced. Stock deriving is the name of the original deriving mechanism that was a part of Haskell since nearly the very beginning. And that's where we're going to start. And actually, if you look at the Haskell report, let me go there. This is the Haskell 2010 report, but it is basically unchanged from Haskell 98. It states that the only classes in the prelude for which derived instances are allowed are EQ, ORD, enum, bounded, show, and read. And then it says something that there are also derived instances possible potentially for library functions, so that are not under prelude, and the relevant type class for which this actually is the case is IX, which is sort of like an indexing type class for arrays, which is these days not that frequently used. But yeah, so those were the original type classes, and the motivation is relatively clear, right? I mean, so equality is a good example. There is an obvious way in which you want to do equality for a data type, but writing out the definition is nevertheless necessary, right? It's not that as if you can write a parametrically polymorphic function that just checks equality once and for all possible data types. You nevertheless have to sort of match on the data type, check whether the constructors are the same, recursively invoke equality on all the components. Doing this sort of stuff by hand is tedious. So if you have a way to get that automatically, this kind of obvious definition, that's very welcome, right? And so these kinds of things, they were the original motivation. So yeah, so let's do one of these. So let's say we have a data type pair of A, which just pairs 2 instances or 2 copies of an A, and then we use deriving EQ. And now in this episode, but also in general, I actually like that very much. I will try to always be explicit about the strategy that we're going to use to derive the instance. So we're going to explicitly say stock here, right? So this is optional. If you don't do it, it'll still work. But we're explicitly saying that we want to do the classic deriving, and like the language extension that allows you to specify the strategy is called Deriving Strategies, which I've enabled up here. But it's actually part of sort of the latest GHC sort of pseudo-standard revision, which is called GHC 2024, which is implemented, I think, from GHC 9.10 onwards. So if you have a very recent GHC, then you don't even have to specify that language extension anymore. You can just use it. Yeah, so if you do this, then you get equality on pairs. And it is perhaps useful if we want to understand a little bit of what the limitations are or how these mechanisms even work, is perhaps useful to see what GHC does with this. And so basically the idea of deriving is just that GHC generates code, and there is built-in magic for the type classes that are supported by stock deriving that generates code. This is not programmed in any way. This is not in a library. This is not using template Haskell. It's separately implemented into GHC for each of the supported type classes. Okay, but we can look at the generated code. So I can say cabal REPL, and I can actually set some options. So I can give a debugging option, which I call, which is called dedump deriv, for telling GHC, or in this case GHCI, to show us the generated code for derived instances. And actually, even though this is an option which normally is mostly used for core code output, and the derived instance code is surface language Haskell code, it nevertheless respects some of the core suppression flags. So I can say something like desuppress all to make the output look a little bit less noisy than it otherwise would look. So otherwise it would have all overqualified names, for example, which are not really very helpful. So
you
now
want to suppress uniques as well?
Let's just live with uniques.
Okay.
I think. So now I have to somehow force recompilation. Yeah. So now if we reload the file, we get something like this: derived class instances. You can see the instance definition that is being generated here, and is very much the one that we would expect. It matches on the two pairs, and it compares the components component-wise. One interesting bit here is that it actually generates an instance declaration with a precondition, right? So it says instance EQ A double arrow EQ pair of A. And there is some sort of built-in heuristic, but based on sort of constraint resolution to some extent, which tries to do the right thing here, right? So, for example, if you define a data type like proxy yourself, which mentions the A on the left but doesn't mention it on the right, and we do the same thing for proxy, then we get now two derived class instances, and actually I think the later ones are printed first, so that this is going to be a little bit lead to scrolling once we have more of these, but you can see here, okay, so the equality is trivial, right? We get two proxies and we basically always say true, but the instance is actually derived in a relatively general way, right? So there is no precondition on the A, and it is even defining a kind polymorphic instance on the proxy here. So like, I mean, that so that it works for regardless of what the kind of the A argument is. So it is trying to be a little bit clever there, right? And similarly, if we have another data type, let's say wrapped proxy A, which wraps another proxy, and we do this again, then here it would again still generate a constraintless type class, because basically sort of it looks at the right-hand side, introduces constraints for these, tries to do some sort of constraint simplification, and then tries to come up with like a good set of constraints, right?
Yeah, so the fact that it's used on the right-hand side does not necessarily mean we need any kind of constraint on A.
No. So here we even use the A syntactically. So that's why I was showing this. It's good that Etzko is highlighting this again, right? Here, I wanted to highlight it's not a syntactic check, right? Here we are not actually using the A at all. But here we are using the A, but because we're using it as an argument to another type, which doesn't actually need an EQA constraint, it is still not being introduced, right? So it does try to be a little bit clever. There are also situations in which it will just fail. So for example, if we have a new A for which we don't derive equality, and then we do a wrapped new A deriving stock EQ, it will complain here that there is no equality instance for new of A, even though in principle, it could generate an instance which just puts the equality of new of A as a precondition, right? So you could imagine that you could, in principle, derive this kind of thing, right? If you ever disagree with GHC on what
all the time
what the preconditions should look like, right? There is a different way of doing this explicitly. You can use something which is called standalone deriving. Standalone deriving, the main purpose of it is actually so that you can give a deriving clause for a data type that already exists independently of the place where the data type is being defined. But another feature or property of this construct is that you basically have to specify the preconditions yourself. So if we want to do this, we can say deriving stock. So the strategy goes here, instance, and then we can say EQ new of A double arrow EQ wrapped new of A. And then it actually complains about undecidable instances not being enabled, which I'll just happily enable, because because that is actually some sort of syntactic check that this constraint isn't smaller than the original one. So it's afraid that the instance search might not terminate, but I'm generally not afraid about this. And then this instance will be accepted, right? And now you could potentially supply the necessary instance for new of A somewhere else, and it might still work. Okay. There are also
one example where something like this might be useful is if there is no general show instance for new of A, but perhaps there might be an instance for a show of or eq of new of something specific.
Yeah.
That might be an example where this would be a useful definition.
Yeah. Exactly. Yeah, that's true. And of course, this is a little bit of a contrived example. I mean, but there are situations in which you basically are forced to give these constraints. For example, if you try to define a derived instance for a GADT, so for example, if we have something like, I don't know, I think I have one here. I mean, this is not about the GADT, and I'm not really going to talk very much about GADTs, but if you have some kind of data type, in this case, this is some sort of an either data type, but it's also indexed by a Boolean, by a Boolean on the type level. So this is something you can still define, for example, a show instance or an EQ instance for, but for a GADT, GAC will generally not be willing to try to infer the preconditions of the instance. So if you try to do something like this, it will actually just bail out and say, I cannot make this for a GADT. Use a standalone deriving declaration instead. And if we do this, deriving stock instance, and in this case, we need EQ of A, EQ of B, but nothing for this type level Boolean, right? Because that also does not appear anywhere in the actual fields. Then we should be able to do EQ choice bool A, B. And this is just accepted, right? And similarly for show, I mean, that would also work. So some type classes tend to be relatively easy to derive for most GADTs, but other type classes such as read or so are generally very difficult. Something where deriving usually stops working. So basically, okay, so I should make one point, right? So there is no, generally, most of the time, there is no real checking like, oh, is the data type in a particular category that I support? What GHC will intuitively do, it will just generate the code, right? And if it fails, it will fail in the generated code. So for example, if I actually try to derive a read instance for this GADT in the same way, I will get some weird error message about like, okay, couldn't match bool with false in the first argument of return, namely no A1, right? But like this is actually referring to generated code. And if we look at this, it's actually nice that the error is only produced during type checking, but the instance is generated before this is happening. So we can actually find the generated instance here, and we can see that it has like return of no of something in there, right? But I mean, I don't really want to go into this, but it's generally the case that sort of the limitations are often becoming obvious by getting error messages about the generated code. GHC is not trying to be extremely clever at this point, but it also means that sometimes when you can make things work for the built-in algorithm, it just still works. One situation where most deriving constructs just fail is if you have existentials, right? So let's actually, I think I have that ready for copying in as well. If I have an existential pair, so say something, I have an A paired with a function from A to int, but on the outside, we don't know what the A is, right? So this is, we have no information if we unwrap this, what type the A is, except that this value of type A and the function, they fit together. So we could apply these two things to each other. So in this particular combination, this is a very useless thing because really the only thing you can possibly do is apply the function to the argument. But there are many nevertheless useful situations for existentials. But if you try to derive anything here, so something like, again, deriving stock instance EQ of X pair, right? It will say that there is no instance, and similarly for show, right? In some cases, you can still make it work because you could just add the necessary constraints here. You could say like, okay, if I can show an A and I can show a function from A to int, which is actually not very likely that I can do that, but if I could do that, then the generated instance would still just work. So again, like, I mean, it's blindly applying the algorithm. If the generated code happens to work for your type, then you're in luck. But yeah, generally, existentials are often a situation where things stop working. Yeah, as I said, like as a final point on stock deriving, over the years, the number of classes have been extended. So if we look at the GHC users guide, it actually says, well, these days there are quite a few more classes than the ones in the Haskell report that you can derive. You can derive generic, you can derive functor, you can derive data, you can derive foldable, traversable, and lift. And these are very useful, and in particular, many of these are type classes that are parameterized over type constructors, so over data types that are themselves parameterized. They tend to be slightly more restrictive in the ways that they can be used, and their exact limitations in practice are also described in this manual. I don't think we have the time now to really get into this, but it is it's interesting to know that you can do these kinds of things. So, for example, we can write deriving stock functor in this position, and it will just give us a functor instance, and that's very useful to know again. And we can also look at the code if we find it, because by now we have quite a few instances here. Here it is. And it like takes the function and it applies it to both components of the pair as expected, right? So this can be really useful. Yeah, but there are interactions here which are detailed in the user's guide with, for example, like if you use the argument as an argument to another type constructor, then there are often limitations where sometimes does no longer work. So let's leave this aside for the time being and move to the next deriving strategy, which is Newtype deriving. So yeah, so historically, the next thing was that there is this Newtype construct in Haskell, right? And you can use a Newtype construct in order to wrap a existing type, and it can be a simple type such as int, but it can also be a more complicated type, like a pair of two things, or an either, or a chained application, or something like that. You can wrap it up in a new type, and unlike a type synonym, Newtype creates like a proper new data type, which needs to be like you need to inject the wrapped value into the new data type using the constructor, and you need to use pattern matching. But the difference between a data type that is written exactly like this and a new type is that the runtime representation is exactly the same. So data types always introduce an indirection, but new types don't. New types, like if you write new type myInt in this style, then a myInt is represented exactly like an int. Now, if it's really represented exactly like an int, then intuitively all code that works for ints should, in principle, also work for myInts. And so, for example, int is an instance of the class num, right, for numeric types. But if you define myInt like this, then it is not an instance of class num. And generally, this is one of the good things of defining new types, right? That you choose which operations you want to make available on this type, and you can start from scratch, right? You can remove all sorts of operations and hide to the outside that this is actually an int and give it a like sort of a new operations. But if you want to, you can inherit or steal from the underlying type arbitrary functionality. Or num is a type class that is not derivable via stock deriving, but because we have a new type here, we can say deriving new type num, and we get a num instance for myInt, right? And we can look at how that instance looks like. And again, we have to search a bit, but we can easily find it because it's pretty big. So this is the num instance that is being derived. And you can see that here, the generation strategy, I mean, it's still generating code for it. It's still checking whether the generated code actually works, and it will complain if it somehow doesn't, right? But the generated code is different. The strategy for generated code is different. If you look at all the different methods that the num class has, and if we zoom in, for example, here on the definition of plus, and let me actually make that window larger just for a little moment, then what is the definition of plus doing? It is just invoking the plus on integers. This thing here is a type application, which basically just says, I want the plus as defined on integers. So this is giving us the addition on integers. And then it's calling coerce, which is some sort of safe coercion function, which is, again, type applied to specify the source and the target type. So it's coercing it from being a function from int to int to int to a function from myInt to myInt to myInt. And coerce is, to some extent, built-in functionality in GHC, which allows between representationally equal types that GHC can prove to be representationally equivalent, having the same representation, it can just coerce between them safely, right? Because like if they are known to have the same representation, then coerce at runtime is just a no-op, right? And the only thing that coerce does at compile time is it does like do the type checking to make sure that this coercion is actually safe and can be applied between these types. And this is done for every single method, right? So it's really just taking the implementation that exists for integers and coercing that into an implementation for the Newtype. And so Newtype deriving is extremely useful. It can apply to potentially all classes, right? But you have to have a class instance for the underlying type. In this case, it is int already, right? If you try to Newtype derive a class instance that does not exist for int, then you will still get a type error. Now, there is also a point to be made here about the use of deriving strategies, right? Because with Newtype deriving and stock deriving both available, you have situations in which you have a choice. So if you consider the show class, and if you consider a Newtype such as myEnd, then there are actually two ways to derive the show class now for myEnd. You can use the stock derived show instance, and that will treat the myEnd just like a data type that is defined in this way. And we can load the module, and I can call show on something like myEnd3, and I'll get the string myEnd3. But I can also Newtype derive the show instance. And if I do that and call show again, I will get the string which contains just the 3 and not the constructor myEnd, because the Newtype derived one literally takes the show instance that is on integers, and stock deriving does something different, right? And in particular for show, but also for other type classes, this can make a difference. If you don't write the strategy, it will pick one, right? And actually, I think the strategy is that if stock deriving is available, it will prefer that. But I really like to be explicit in cases like this, right? So this is a nice advantage of the deriving strategies extension.
So one thing that's maybe worth pointing out here is that if you go back to Newtype deriving for stock, the output is going to be just 3, right, with no myInt. Now, generally, we want the show instance to generate valid Haskell code, right? The string that it generates should be like usable as something of type myInt. But because Andres also derived num, that is in fact the case. Like you could write 3 of type myInt. So that combination of num and a Newtype derived show instance can be quite useful. For example, I do this quite a bit with strings. Like, you derive a string instance, and then you don't need the constructor, and you get the output slightly. Sometimes it can make the output more easy to read.
Yeah.
While still satisfying the property that the string that it generates is valid Haskell. It's a useful thing to know.
Yeah. Now, Newtype deriving also has its own limitations, and again, this is something I want to mention briefly, but I don't have the time, I think, to, like in this episode, to go into the details. But if you consider something like this, which is a wrapped maybe type, you can, for example, Newtype derive the functor instance of the underlying type, right? I mean, again, this would also work with stock deriving, but we can just say, okay, well, maybe of A has a functor instance, so I should be able to steal that. But if you try the same thing for traversable, and maybe has a traversable instance as well, then you get a weird error, which has to do something with the fact that traversable, if you look at the, again, I'm not going to
go into too much detail here.
Too much detail here, but nevertheless, I want to point out what it is about traversable that is causing the problem. You're having these parameters f in the functions of traversable, which are having an applicative constraint. In this case, doesn't matter, but it's not the f that is the type that the class ranges over. It is a separately quantified f. And that means that we have to basically establish that f of maybe A is representationally equivalent to f of my maybe A. And that is simply not always true. because due to, for example, GADTs, it is possible in general for an f of maybe a to have a different representation at runtime than an f of maybe a. And this is why in general it fails. There is a whole mechanism in GHC that tries to make this more precise, which is called roles, which we could also potentially do an episode at some point. But I think Richard Eisenberg has some videos about this because he has also been working on roles for quite a bit. So you might want to look there.
I have one question for a viewer for you. It's a slight tangent, but perhaps you can just say a few words about it.
Yeah.
Sure. So Nicholas asks, why not have every data type with exactly one constructor behave like Newtype? Why expose this choice in the language? And in fact, for example, the language clean, which is like Haskell, does exactly what Nicholas is suggesting here. So
there are some, I guess, I mean, I'm not sure. I think it is a defensible design choice. One could do it. But there are some differences in which data types and Newtypes behave with respect to laziness, which come exactly from the fact that like Newtypes don't have this additional indirection. And having this special behavior automatically be applied for one constructor, one element data types might sometimes, like in the best case, lead to confusion, but in the worst case, actually lead to unwanted or bad behavior in such situations. But I cannot on the fly give a good example there. But
maybe what I would say is that it's useful to state intent, right? So when you're saying Newtype, you're really saying, I want this thing to be representationally equal. And then somebody else is not tempted to just add another constructor or something like this. Like you're stating very clearly what you want. Whereas if it is a data type with one constructor, maybe somebody else changes it without knowing your intent. And now suddenly the properties of your program changes. So I think it's good to be explicit about this.
Yeah, I think that's a different angle, which I also totally agree with. Yeah. Okay. Yeah, but great question. Okay, so I'm sorry for being slow once again. So I was actually not expecting that we're above 30 minutes at this point. But like the third one, Anyclass, is actually relatively short. Like, I mean, we don't have to say very much about it. But historically, the motivation for Anyclass has been generic programming, data type generic programming. And I am actually planning to do one of the next Unfolder episodes about something related to data type generic programming. So perhaps we're going to say a little bit more about that. But what Anyclass really is designed for is a situation such as this. I have a simple example here. If you have a class, let's take a simple example, class 0 of A, right? And we have one method which is supposed to give us some kind of 0 element. There is like a way to in GHC to give default implementations of methods. But for 0A, we cannot really easily give a default implementation for an arbitrary A. But we can say, for example, 0 could be defaulting to 0 if we additionally know that A is actually happens to be a num, right? But we don't want num to be a superclass of 0 because then we couldn't define instances for anything else anymore. And in such a case, I can make use of a language extension which is called default signatures. And I can write sort of a second type signature prefixed with default for 0, which says, okay, if I have this thing, I need to enable the language extension, then I can give a default of 0 equals 0. And now, if you have a class which is completely filled with methods that all have either like completely general defaults without constraints or such default signatures that have constraints, well, you can effectively define an instance for this 0 class for a type such as myInt, for which I previously defined a num instance, right? Without any method definitions, because they're all filled with their defaults. And just to make that look somewhat nicer, or to look at more in line with other deriving in constructs, this is what deriving any class offers. So if you, for deriving any class, you have to still enable a separate language extension, which is called deriving any class. But if you do that, you can, instead of this empty instance declaration and any empty instance declaration, you can also just write derive any class 0 here. And yeah, now it's complaining that I haven't got derive any class enabled, but if I do that, that's it. And this is all that there really is to say about deriving any class. I mean, every any class deriving thing could be replaced with an empty instance declaration, and you can really do that for any class. It does not enforce that the class is one that has defaults for everything. But if you use it for a class that does not have defaults for everything, you are getting warnings, right, that you have uninitialized methods. Similarly, for classes that do have defaults for everything, but have a minimal pragma in GHC that specifies that you define something. Like, so like a weird example, for example, is if you do any class deriving of EQ. EQ is weirdly defined in GHC and has two methods, one which is equal, one which is non-equal. Then there is this pragma which says you should define at least one of the two explicitly. And then they have defaults that basically mutually recursively say that the default for equals is that it's the negation of not equals, and the default for not equals is that it's the negation of equals. So you do get this warning, but if you actually try to run this thing, like if you try my_n3 equals my_n5, it will now loop, because these methods are calling themselves. So it's good that we get this warning, and these warnings about not explicit implementations being given, they should be taken seriously, and any class should really only be used for type classes that have defaults for everything, right? Mm-hmm. Okay, that leaves us with the final strategy, which I think is very cool, but we've also already done an episode. I don't exactly remember the number, but we've done an episode on monads and deriving via, where we've already used this once. But in the context of this episode, I think I'm primarily going to say the mechanism is very, very similar to the mechanism for Newtype deriving.
Thank you.
I
was close.
The realization is that, well, why can we steal the instance for int in order to use it for my_int? Well, because int is representationally equal to my_int, which is what a Newtype just establishes. But other, like more distant types, can be representationally equal as well. Like there can be arbitrary Newtype chainings and unchainings between two types, right? And they're still, in the end, representationally equal. And basically, that is the kind of generalization that deriving via allows. So I could, and again, I'll just do that up here. For example, even write the Newtype derived num instance using deriving via instead by writing deriving num via. And then here, I have to say explicitly from which type, which has to be representationally equal to my_int, I want to get my instance. And in this case, that would be the type int. And again, I need to enable the deriving via language extension. The normal use case for this, and to understand sort of the full power that this gives you, you might, we might either want to watch the other episode, or you might want to do another episode, or you might read other blog posts or papers about this. But the normal use case for this is the other way around, right? So is that you define a new type and attach some functionality to it, which you can then use programmatically. And I want to show, to end the episode, I want to show one example from one of ETSCO's libraries, actually. But it's just a representative example. This is the Recover RTTI runtime type information library, which does some dark magic in order to give you the ability for debugging purposes to show data, even if it normally is very difficult to define a show instance for it. And that
only for debugging.
Useful. Yeah, you should not use that for other purposes, but for debugging purposes, it can be very useful, yes. Right? Mm. It directly inspects the heap in order to produce some textual output, and and just as a representative example, so with the advent of deriving via, you find more and more libraries that provide things such as this one here, which is from the documentation of this Recover RTTI library, where you have a Newtype here, which says, oh, this is intended to be used with deriving via. And the way this works is that there is a show instance, right, defined by the library for anything that is of the type anything to string of A. And the actually, you can even see that from the constructor here. The anything to string of A is simply wrapping a single A, right? So anything to string of A is representationally equal to an A, but it has this library-defined show instance, right? And there's no constraint, no other constraint on the A. So basically, you can use this to get a show instance on any data type without any further constraints. And we can, in order to demonstrate this, we can try to define a show instance for our existential pair, which was like one of the things which were really difficult to previously show. So where was that? X pair. All right, so let's do here. Let's say deriving show via anything to string of X pair. All right, so this is my other data type, which is representationally equal. And this one does have a show instance that is defined in the Recover RTTI library. So I'm getting the show instance on X pair via this one. And sorry, I think I can also try to load this once more and look at the instance. It's here. You can see this is what I meant with, like, the mechanism is really similar to generalized Newtype deriving, because it's doing exactly the same thing, only that the source and the target types are now different, right? So for show itself, it is invoking the show function on anything to string of X pair, and then it's using coerce again to go from the show function on anything to string to the show function on X pair. And because these two types are representationally equal, the safe coercion type checks. And we can also try it out. So let's try to show an X pair of, let's say, 3 and the identity. And now we actually get a string. So Recover RTTI does not do infinite magic. So for functions, it does not somehow magically give you the lambda term or something like that. That would be really difficult because, like, I mean, it's code at runtime, right? But it does show fun. But the 3 is printed as a 3, right? And if we would put something else in here, like, I don't know, a character and then the ORD function. Oh, for ORD, I have to import data character. Then it would also still work. Yeah, but I mean, this is just like an example, but the general principle here is that libraries can store general principles, like, of how to define instances for certain data types independently of the type classes, therefore, right? You wouldn't want to make this kind of principle the default implementation for the show class so that you could use any class deriving, because it's really for a specific purpose, and there might be, like, other defaults or other implementations for other purposes. but you can still like give it a name and make it programmatically usable using this mechanism deriving via. And yeah, that's quite powerful, and there are many cool applications possible. I think, yeah, we're far over time.
We have two final questions.
Okay, yeah.
One is there any extension which enables every derive XYZ? Because it gets annoying.
No, I mean, so some of them are already a part of even GRC 2021, which was the predecessor of GRC 2024. So I think derive functor, derive traversable are already part of GRC 2021. Deriving strategies is now in 24, perhaps even some others as well. So in general, many of these gradually become more established. But otherwise, no. I mean, what you can, of course, in general do is rather than writing the extensions in every single source file, you can, if you have a Cabal file, you can define the default extensions for a project. And you can give a list of extensions there, which is automatically enabled for all the files in your project. Some people don't like that because it makes it less obvious which language you're actually working in if you're loading up an arbitrary file, right? It's further away than if you just have to look at the top of the file. But I think it is a sensible thing to do if you're developing, for example, larger application and you want sort of to establish a uniform baseline for all your modules. I mean, there are certain language extensions I would never enable by default, but in general, it is a way to solve this problem. Yeah.
Yeah, one more question from the same person, and then actually we have a third question that just came in.
Okay.
Does the call to coerce have any runtime penalty, or does it get inlined basically?
The call to coerce does not in itself have any runtime penalty because the call to coerce eventually completely disappears. I mean, it simply does not do anything at runtime. Now, statements such as this are always a little bit difficult because, I mean, GRC has a very clever optimizer, and obviously it still exists in core, right? And core is where all the optimizations happen. So to actually prove that the presence of a coerce does never prevent another optimization from firing that would otherwise fire is very difficult. And I actually doubt that this is the case. I mean, like I think there are almost certainly cases where this is still true. But coerce was introduced in order to do things with Newtypes at no cost that otherwise would have a cost. The classic example is, say, if you want to coerce a list of ints to a list of my ints, right? Then doing that via coerce is free, right? I mean, is a no-op. But if you didn't have coerce, then you would have to actually traverse the list and do a map over the list that applies the Newtype constructor everywhere, right? And there is no other way to do that in a type-safe fashion. And prior to coerce, for these reasons, people would then actually use unsafe coerce in such situations, which is, of course, safe in such a situation, but you feel bad about it because it's easy to get wrong if you refactor or change anything in your code because there is no check. And coerce keeps this safe and compiler checked and is generally free. Yes. Okay.
All right. Final question. Regarding Newtype and stock deriving, when both strategies are possible and give the same behavior, is there any reason to pick one over the other?
I don't know. I think possibly. No, I don't know. I mean, so you could argue code size could be slightly different, but even that doubt it, because like for most of the time, like if you have a single constructor, a single argument data type, the stock derived instance will not be extremely large, and the other one will just be a shallow coercion wrapper. I don't know if they really give the same behavior. I don't immediately see one reason to prefer one or the other. Perhaps there is, perhaps somebody else knows, but I
can't think of one either.
Yeah.
Okay, that's it.
Okay. Then
so thanks everyone for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. Feel free to leave any more comments in the chat. We'll leave it open for a few more minutes, and otherwise feel free to pop them in the video, like the comments below the video, and we always keep an eye on those and try to answer as many of them as we can. So yeah, thanks very much for watching.
Yeah, thank you.